Okay, so today I'll cover two exercises, 9C and 9D. So we'll start with differentiating x to the power of n, where n is a negative integer. Okay, we looked at before when n was just a positive integer. Just to lead you ahead, when you differentiate x to the power of n, the actual power, it doesn't really matter if it's positive, negative, a fraction, or a decimal, the rule will still be the same. Okay? So, it's the same as before, the formula will be the same. Hang on, there's something that is annoying me here. Hold on, bear with me. Yeah, I'll need to remove this one. Okay, so when you differentiate, so your function is x to the power of n, okay, the derivative is nx to the power of n minus 1. So again, you have a coefficient n that's coming from your original power, and the new power of the derivative is 1 less. Okay, so if you start with a function that is a quadratic, the derivative is linear. If your function is a linear, the derivative will be a constant. If you follow to that, if your function now is a constant, so any value, so fractional, whole, positive, negative, that derivative is going to be 0. Okay? So to find the derivative of an expression, you look at all the individual terms. Okay? So as from the previous slide, the constant here is the last term. The derivative of that one is going to be 0. Okay, so you have 4 different terms. You will apply the formula. Okay, I just realized, let me move the chat over. No, actually, I'll leave the chat over here because I need to. Actually, I know I can look at it over here. Yes, I am recording. Okay. Just be mindful when you send me. I'll move it back here, but just be mindful. It's alright. It's all about work anyway. All the private chat here will be part of the recording, so just keep that in mind. Unless I'll move it over, I'll think about it in a second. Okay. All right. So going back to this, you will look at your function. You have 4 different terms, so you look at all the different terms you apply. So x to the power of 4, the 4 power becomes a coefficient, and that will become the new power is 4 minus 1, which is 3. Okay, you will do the same with all the others. So notice that's negative, so you have a negative 3 coefficient. The negative 2 remain a factor. Okay, and now the new power, just be careful again, you deal with negative number. Negative 3 minus 1 is negative 4. Okay, then you simplify, you rearrange your formula, so you have your negative 2 times negative 3 is positive 6, and here you have a negative 1 coming from that one, so that you will have a negative factor here. Okay? Alright, another example. So it's an application, it's a little bit worded, but the mathematical application is just applying the formula for the derivative of x to the power of n. So find the gradient of the tangent. So the gradient here it gives you a hint already, is you need to figure it out, the actual derivative. Okay, but because it's a gradient value, once you find the derivative, which is a function, you will have to substitute a value for x to determine the actual value of that derivative. So the function is given to you here. Notice the domain, just be mindful always with the domain, it excludes 0. Now the point will be 1, 2, so the value x equals 1 will be used to substitute into your first derivative. So you have your function here. Here is a polynomial function, and you need to change the power to a negative. Okay, so this is equivalent to x to the power of -1. So with the working out, you will have a x squared. So the derivative of that will be 2 times x to the power of 1. This second term, it's x to the power of -1. You will write it as a -1 coefficient in front, and that -1 power minus 1 will give you a -2. Okay, so you will have 2x minus x to the power of -2. You substitute x equals 1 into your derivative. You simplify your expression, that gives you 1. So the gradient of the curve, I'll move that out of the way. So the gradient of the curve is 1 at the point of the coordinates 1, 2. Okay? I need to close that. So I'm just trying to manipulate my windows. Even with 2 screens, I still have issues to find enough space. Okay? Alright. So another example, again, it's just getting you to manipulate negative powers. Here it's given as a negative power. Do remember it could be given as a fraction. So it could be 1 over x to the power positive 3. So turn it back into a negative power so you can apply the formula of the derivative. Okay, so your derivative here will be -3 times x to the power of -3 minus 1. -3 minus 1 gives you -4. That will be -3 times x to the power of -4. And here they just rewrite it with a positive power. Okay. So notice, because the power here is even, what it means is that derivative, it doesn't matter what value of x you use for the domain, because you have an even power, that is going to be positive. So by multiplying with a negative, that derivative is always a negative. And what it implies as a function is, if you go back to the sign of the derivative, being the derivative being negative means the original function f is strictly decreasing. Okay. Sorry, any question? I'm just checking the chat. Louis, it doesn't really matter. You can write it as a negative or positive power. Just be mindful they're both equivalent. Alright, so let me continue. So that's the finishing up to 9C. So you can just go on with, after I finished, you can get started with those questions. The really skill questions about really applying those with negative integers. So they will have 2 forms, either with the positive in fractional form or with the negative. Okay. Now let's look at the graph of the derivative function. So it relates again to a strictly increasing and decreasing function. Okay. And Josh, you remember you were asking me about the sine function, sorry, the sine graph. Using the first derivative is also useful to determine that as well. Okay. Alright, so we start with an easy function. So let's say you have a linear function. Okay, so that's your linear function. So it's in the form mx plus c. If you do the derivative of a function mx plus c, the c will be 0, but the derivative will be equal to m. Hence, that is why the derivative will always be a constant, so will be equal to m. So if you look at that function here, can you tell me the value of the gradient here? So it annotates the 2 intercepts. correct? It is 1. So when you differentiate that equation, you don't, so anyway, the equation is y equals x plus 1. So if you differentiate that, the derivative is going to be equal to 1. And you write y equals 1. So the graph of the derivative is just a straight line that is horizontal going through the point on the y-axis, y equals 1. Okay? So for a straight line, depending on the sign, it will be a constant. The derivative is a constant, and a constant graphically is also a straight line which is horizontal. Okay? Now, if it's negative, the gradient here is -1. So again, it's a horizontal line, but notice it will go through the y-axis at the value -1. So again, its position will depend on the value of the gradient. Okay, so again, if it's increasing, it's going to be on the positive. The derivative will be on the positive side as a horizontal line. If it's negative, it will be on the negative side of the y-axis. Okay. If it's quadratic, so the highest, the degree is 2. If you differentiate degree 2, that will give you a degree 1. So that's degree 2. The derivative will be a degree 1. The general formula is mx plus c, so it will be a straight line. Okay, so in that form, it's going through 2. Now, what is the gradient here at that turning point? Correct, it is 0. So just be mindful with that. So when you look at your turning point here, that tells you that derivative, it's going to go through at that x equals 0, it will go through the origin. It will be y equals 0. Once you determine that, you can see on the right hand side the gradient. If you place a straight line here on this side, you will see that it's increasing, so it's going to be positive, and here it's going to be negative. So what you have is, at that turning point, you have your x-intercept for the derivative, which is a straight line. On the right hand side, it's increasing, so the derivative has to be positive, so it's going upwards because again it's a straight line. And then on the other side, it will be negative. Okay? Yes, Elia, what are you on about with -0? Or is that just a dash? Alright, so that's the idea. Okay, so for we looked at a linear function and a quadratic function, and we move on to, yep, okay, so that was 0. So for a cubic function, cubic will have 3 terms: x cubed, x squared, x, and a constant. You differentiate that, that will give you a quadratic. So a full quadratic will be in the form ax squared plus bx plus c. And then depending on the situation, some of the terms might not be there, and so on. Okay. Alright. To the quadratic, we'll have potentially how many intercepts for a quadratic function? So we can have a maximum of 2. And when you talk about x-intercept for a quadratic function, it means the quadratic function is equal to 0. And do you remember, in terms of derivative, it represents the gradient of the tangent of the original curve. So the original curve is coming from y equals f of x, which is a cubic. And notice you have 2 turning points. So those 2 turning points at x equals -1 and x equals 1 will help you to determine the gradient of 0 for the derivative, which is your x-intercepts for the derivative. So the derivative will be a parabola. So again, a parabola can be upside down or U-shape. Okay. So what you would do is place your x-intercept. I know if I click it's going to give you the whole curve, but what you do is first you concentrate on your turning point here. That will give you your two x-intercepts, -1 and 1. Alright, and what you do is, for example, let's look between -1 and 1. You look at your function, the way the cubic behaves. So it's going downwards. As it's going downwards, what it means is if you take a point in between here and you pick a point here and you try to imagine the tangent, it's going to go down. So as it's going downwards, it means that it has to be negative. Your quadratic has to be negative in between. Okay, and on the other sides, on the left of -1, on the right of 1, the function is increasing, so the cubic is going upwards. So what it means is the quadratic, which is the derivative, will be positive here and positive above x equals 1. Okay, now with the information from your cubic here, you do not know that value down here. There is no way you can find out. There's not enough information from that the graph of that cubic, which is fine. Okay. Alright, so if we look at a different cubic function, so a cubic function will have different, it can have a certain number of intercepts, can have 1, 2, or 3 x-intercepts. So in a situation where it's only one intercept, if you imagine your derivative and the function is always increasing, what it means is the derivative is always positive. So again, a cubic will have a derivative that is a quadratic. In that situation, a quadratic to be always positive, it will mean that it's above the x-axis. Now, it's also equals 0 at that point of its stationary point of inflection. So here you have a gradient of 0. That is why the quadratic is slightly touching, it's actually touching the x-axis at the origin. Okay, I think, yep. Any questions? Okay. So going back to a quadratic function, so if you have a vertex, which is your turning point, so vertex is also the synonym to a turning point, x equals a and y equals b. All right, what you can figure it out is for the gradient is at that turning point is equals 0. That's why for x equals a, the derivative, which is a straight line, will cross the x-axis. That will give you your x-intercept. Okay, so just to repeat that. Also on the right hand side, your function is increasing, so the derivative is equal to the derivative is positive, and on the other side, as you're crossing the x-axis, that left side will be negative, which is what you have for x less than a. The derivative is less than 0. So here it's on the left hand side of a, the function is strictly decreasing, and then on the other side will be strictly increasing. Alright, I'll probably use paper for that. I'll use the overhead camera. So you have your function here. By the way, it's a hybrid function. If you, for specialists, it's a modulus function. Draw a sketch graph of the derivative of f when the graph of f is illustrated here, and indicate when f prime is not defined. Okay, so I'll just give you a minute. Try to jot down the graph of the derivative, and I'll get to the answer in a minute. Yes, the application will be in physics with the derivative. So when you have the displacement, the first derivative is the velocity, and if you differentiate again the velocity, that gives you your acceleration. Now there are other applications in other area of science. It's also quite useful in modeling. When you differentiate, you can determine the rate of change of any function. Yes, Louis, 0 is your answer for, can't be for the current question. The current question is about graphing. Or was I a little bit late? Alright, can I move on? Now, before I move on, can you tell me where it's the last statement? So indicate where f prime is not defined. Not Carly, it's not when x is greater than 2. When x equals 0, which is correct. So if you look at the graph here, and I'll get to the graph of the derivative. So you have a straight line here on the left hand side, and you have also another straight line on the right hand side. So here on the left hand side, to determine if you had the function rule, you would just differentiate using the rule of differentiation for x to the power of n. In this situation, it's you look up at your rise over run, so it's a 2 over 1, so that's 2, and here it's going downwards by 2 and 1 across, so that would be negative 2. Okay, so when you graph your derivative for x less than 0, you will have a gradient, a straight horizontal line of y equal 2. On the right hand side, for x greater than 0, the line is going negative, so the derivative will be y equals negative 2. And notice that if you get really close to 0, from the right it's negative 2, so it's, remember the notation with limit. If I was doing x approach 0 from the right, it will be negative 2, and if I approach x from approach 0 from the left, it will be positive 2. Now 2 and negative 2 are not the same, so the statement is the derivative does not exist at x equals 0. To exist, from the left and the right, they must be the exact same value. As 2 and negative 2 are different, then we can conclude the function is not differentiable at x equals 0. Okay. Another way is saying the derivative is not continuous. Okay, continuous, the idea is if you were to draw it and you use your pen, if you have to, you draw it. So you have your pen that goes over here, and because you have to go to negative 2, you lift your pen. The fact that you're lifting your pen means you're not continuous anymore. Okay, does it make sense? Alright, so talking about differentiability, it's what I just finished from the previous example. It's talking about, is a function, the derivative, and you look at the derivative and the function f is your original function, is it differentiable? Okay, and in this situation it's not differentiable at x equals 0. We're going to look at the general way of doing this. Okay, so you have some functions are not differentiable at all values, so you will create a situation of a hybrid function. So you have a linear function for positive x, and for negative it will be a quadratic. What you need to do is you differentiate, hang on, I don't want to do, they use a limit. Okay, that's kind of a long way, but okay, let's go with this one. So if you do the limit for the right hand side, for x, that gives you h over h, that gives you a value of 1. Okay, and for the quadratic part, again, it's a limit when h converges towards 0, and for x equals 0, that gives you h squared over h, which is h. When h converges towards 0, that gives you 0. Notice those two values are different. Okay, so the gradient does not approach a unique value as h converges towards 0, and as we say, the limit of that gradient is, again, that's related to the first principle. And when h converges towards 0, because it's not unique, then the function, the limit does not exist, because you can't choose between 1 or 0. Okay, it needs to be the same amount. So the final statement is the function is not differentiable at x equals 0. Why am I doing this? Going back to now. Okay, hang on, there's a statement from earlier. Is that graph for gradient basically? Correct. So but that might not be constant. So again, your the graph of that gradient, as defined, the derivative is the gradient of the function of the tangent. So it's the gradient of the tangent as you move along different values of x. Okay, so that's 9C and 9D.